The main objective of this lab was to observe and analyze the motion of an object moving with constant velocity. There are two dimensions that play a role in velocity: magnitude and direction. The magnitude of velocity is speed, so it is important in this lab to create a scenario in which an object moves at a constant rate in the same direction throughout the time interval. After doing so, a computer program was created that would accurately depict the real-life scenario. In order to obtain data about this scenario, Tracker was utilized, which analyzes the video frame by frame. In order to do so, we must provide information to the software, specifically the axes and the diameter of the object. In this situation, orienting the axis at the center of the object in the first time frame results in the object moving along the positive x-axis throughout the time of interest. Also, due to the fact that the object was originally at x equals 0, the data collected from Tracker represents the displacement of the object. Furthermore, a calibration stick was used, in which manually entering the diameter of the object provides Tracker with a reference to record measurements. By doing so, Tracker can then collect information about the movement of the object with relation to time. It is important to note that if the orientation of the axis was different, the only thing that would change will be the direction the object is moving, such as in the negative x direction. However, the velocity would remain constant. In order to replicate this data using computer programming, a fundamental principle, also known as the momentum principle, comes into play. The momentum principle is utilized in order to update position and velocity of the object as time progresses. In computer coding, this is done using a while loop. These are the steps that are utilized when trying to update position and velocity using the momentum principle. First, it is important to calculate the average velocity. I did so by picking two data points recorded from Tracker and used the equation average velocity equals change in x divided by change in time. This formula is valid in this scenario due to the fact that velocity does not change throughout the video, so picking 2 times and the corresponding distance traveled is sufficient when trying to determine the velocity throughout the entire video. In the code, the initial position of the object is determined using data from Tracker. As mentioned previously, I also calculated my average velocity with the same data. FNet has a magnitude of 0 in the code due to the fact that FNet is equal to mass times acceleration, and the object does not accelerate throughout this time of interest. Therefore, in the while loop, the velocity of the ball will not be updated due to the fact that the current velocity is added to FNet divided by mass times delta t. Since FNet is 0, velocity will remain constant throughout. However, the position of the object will be updated using the equation r future equals r now plus v average times delta t. Other important factors to consider were delta t, which was also provided by Tracker. After the code is run, the output is fairly similar to the real-life scenario, but more information can be obtained when comparing the actual data points to the predicted data points. As you can see in the output, the predicted data points indicates an extremely linear line between time and the position of the object. The position time graph compares the two sets of data, and the predicted versus actual positions are fairly similar. The data indicated by the orange line is the predicted position of the object as time progresses, which is fairly apparent due to the fact that the line is perfectly linear. The discrepancies could occur due to the fact that it is hard to create a scenario in which FNet is always precisely 0. For example, the force of friction likely was present during this situation. Therefore, due to the fact that the object started moving because of an external force, it is hard to know if that external force was with the right strength so as the force of friction would be cancelled out. Therefore, it is difficult to know with 100% certainty if FNet remains 0 throughout the entire video. In conclusion, the computer program is much more accurate when attempting to collect data about the movement of an object with constant velocity.